Welcome to week 12 and lecture 11, which is going to be on decoders, encoders, and the arithmetic logic unit. As we said in the previous lecture, weeks 10, 11, and the current week 12 are closely related. We've been through examples of using the XOR gate, we've talked about adders and subtractors during week 10, then last week during week 11 we talked about comparators, multiplexers and demultiplexers, and during this week we're going to talk about encoders, decoders, and the arithmetic logic unit. So let us start with decoders. A decoder is a multi-input, multi-output logic unit that converts coded inputs into outputs. This is how a standard 2 to 4 binary decoder looks like. You got the two inputs here, and based on the combination of bits inserted here, only one of the four possible outputs is going to be activated. And of course, you've got something you've seen earlier on also with multiplexers, an enabling bit. So 2-bit words come in as input. If the decoder is enabled, then only one of the four outputs over here is going to be activated. And this is the truth table. As you see, if the enabling bit is 0, we don't care about the input, it's irrelevant. The output is always 0, nothing is activated. Nevertheless, for the rest of the combinations, you see that only one of the inputs is going to be activated each time. This is how it looks like as a circuit. And as you could guess, the enabling bit has to be passed to a final AND gate so that an output is enabled if and only if the enabling bit is equal to 1. Having that said, a question to pose to you is, are Y0 to Y3, in other words the outputs here, active high or active low? The answer to this question is that only one of these outputs will be active high based on the combination of inputs present when the decoder is enabled. In other words, this means that the decoder detects a particular code only. As we have said in the past, NAND gates are generally faster. Therefore, a decoder can be constructed with active low inputs. The only thing you need is to negate the result of the AND gates at the end, which is why we suggest using NAND gates. What is different in this case is that the enabling bit is 1. If it is 1, then you ignore the inputs, and the outputs should be ignored because they're always equal to 1. And what you care about is every other combination, everything else that comes with an active low enabling bit, and the decoded result is seen here as active low output. In other words, a 0 result for the activated output. Now, a similar question to a question we've seen also for multiplexers. Can you use 3 to 8 decoders in order to build a 4 to 16 decoder? The answer is yes. As you can see, the 3 first bits are passed straight to the first and the second decoder. And the 4th bit is used for enabling or disabling, if you want to, the other two decoders as a whole. So whatever value enables the first decoder will surely disable the second decoder, and vice versa. This makes sure that only one of the outputs will be enabled in both decoders. As we've seen in the previous examples, if you have a decoder that has n input bits, then it's going to generate 2 in the power of n possible outputs. Each output is asserted for a unique input combination. If you give a different combination, you will activate a different output of a decoder. And each output will correspond to a different mean term in the corresponding truth table. Any logic or Boolean function can be represented by a decoder followed by an OR gate that sums all of the minterms. If you think of it twice, this makes sense. We have previously said that all Boolean functions can be represented as a sum of products, which represents each of which represents a minterm. Therefore, if the outputs here represent minterms, the only thing you need is to put an OR gate at the end, and then you have a sum of all the minterms. Let's see this example here. This is a full ladder example. This is the truth table we want to implement with the decoder. Let's use this one as an example. In this case, the carry in is 0, x is equal to 0, y is equal to 1. The result of the sum is 1, and there is no carry out. If we go to another case, like this one over here, if there is a carry in and either of the two is equal to 1, then the sum is 0 and the carry out is 1. The same applies for minterm 5 and 6 here in this case. And for the most extreme case that you got both a carry in and both bits being equal to 1, both the sum and the carry out should be 1. Now let's see how that would work in practice. We have 3 bits that come here as an input, x, y, and carry in, and we got 8 different possible outputs. Notice that for the first minterm, we ignore the output. A sort of saying that the carry in can be used as the enabling bit. Now we take the outputs from here and we pass them through some OR gates. The configuration which is applied here maps the result of the sum in this particular case. So we're selecting all the minterms for which the sum is equal to 1, that is minterm 1, 2, 4, and 7. 1, 2, 4, and 7, as you can see. As for the carry out, we have again an OR gate, and again we are summing all of the minterms for which the carry out should be 1. In other words, 3, 5, 6, and 7. Let's see it also here, 3, 5, 6, and 7. Wrapping up everything together, with the simple example, we have verified that any logic function can be represented by a decoder followed by an OR gate that sums all of its minterms. In this case, we have 2 logic functions, one for the sum and one for the carry out. And we use the same decoder to implement them. As you may have noticed by now by yourselves, there is a resemblance between demultiplexers taught in the previous lecture and decoders. A decoder and its enabling bit can be considered as a demultiplexer. Let's see together why. The input, which is passed to a demultiplexer, can be the information which is now passed as the enabling bit to the decoder. And the selection bits over here, they can be used as the input of the decoder. So this information here, the enabling bit, is directed to one of the outputs over here, depending on the selection, which in this case would be the 2 input bits passed to the decoder. It's exactly the same as in the case of a demultiplexer. Like the first selection over here, 0, 0, if you just follow the paths, they will be first negated to 1 and 1, it will be passed here, and the result, if you make the calculations, will be E. In other words, the information that we passed through the enabling bit. If you try yourselves different combinations like 0, 1, 1, 0, and 1, 1, you'll see that each time one of these gates is enabled. Last, manufacturers refer to n-to-m binary decoders like this one over here, and 1 bit to M outputs demultiplexers as decoder/demultiplexers integrated circuits. The reason is obvious, because they're equivalent. Let us now see together an example of an MSI 328 decoder, and more specifically the medium scale integrated circuit 74X138. Notice a few interesting things here. These are the internal signals. Now we have 3 enabling input bits, and we get as input a 3-bit word. Notice that the 2 out of the 3 enabling bits are negated before given as an input. So the internal signals here are actually the negation of what comes in here. And as for whatever comes out as an output, it will be the negation of the corresponding results of the output here. This is more clear here. For example, Y0 as an output will be negated and will pass to the external world as Y0 underscore L. So if this is 1, it comes from a result which is equal to 0, and so forth. Now let's understand together why some of the specialties of this 328 decoder. The first thing to say is that if the first of these enabling bits, the one that comes through gate 1, is equal to 0, then we ignore. We do the same thing, we ignore, and the output is not enabled if the second gate is equal to 1 or the third gate is equal to 1. For any other combination, the 328 decoder is enabled and only one of the outputs will be enabled. And we have a low state logic, as you can see here, because of the negation here at the end. Now, if you are interested to see how this is internally organized, this is on the next slide. And as you can see, the first enabling bit is negated while the other ones are not. Now notice that there is a reason for this configuration. This is in low state while these ones are in high state, because as you're going to see on the next slide, this allows to cascade together more than one 328 decoders in order to formulate bigger decoders. Now let's see together the case of cascading 328 decoders. This falls in a broader category when you're using multiple binary decoders in order to decode larger code words. Now these two decoders over here, when they put together these two 328 decoders, they result in a 4 to 16 decoder. And let's see how this works. The most significant of the bits, in other words N3, defines the following. If N3 is equal to 0, then the higher decoder, U1 over here, is enabled. So if it is 0, it will be negated and passed here as input, which is going to make the first decoder enabled. Nevertheless, if it is equal to 1, then it will disable the first decoder, but it will enable the second decoder. As we've seen in the previous slides, when the first input is equal to 1, then the decoder is enabled. So the most significant bit here is important because it defines which of the two decoders is going to be used, and then the rest of the combination alongside with the other bits defines what is going to be the decoder's output, depending on which of the two decoders is enabled. Now let's talk about encoders. As you can imagine, an encoder does the exact opposite job of a decoder. So this means that you get a number of inputs and only one of them is enabled at a time. And according to the input that is enabled, to the unique input that is enabled, you got a specific output coming out. Another thing, as you can imagine, since it's doing the exact opposite operation than a decoder, then the number m of inputs has to comply with what you see over here. M must be at most 2 in the power of n, where n is the n-bit word that is outputted. And of course, you can treat each of the outputs here as a function and then use the mean terms, like for y0 over here. By using the mean terms, of course, you can write it down as a Boolean algebraic function. But as you can see, there can be ambiguity. What happens if more than one of the inputs is enabled? Yes, it's a state of ambiguity in this case. Therefore, we need to assume that the system ensures that only one input is activated at a time. And each corresponding output can be written as a sum of products correspondingly. And this works if and only if only one of the input is asserted at a time. Apart from the ambiguity we've seen in the previous slide, there is again another ambiguity. Even if the system ensures, as we said, that only one input is activated at a time, as you can see here, the first bit of the input word is ignored. This creates an ambiguity, because you can have an output that is equal to 0, 0, 0, irrespective of the value of the first input. And that is another ambiguity. Now, let's jump to priority encoders. What is a priority encoder? Well, it's a circuit that compresses multiple binary inputs into a smaller number of outputs. And in order to make this work, what happens is that if 2 or more inputs are present at the input of a priority encoder, then the input with a predefined higher priority is going to be encoded. This is reflected in the truth table that you see over here. This means that only the bits with a higher priority are encoded and the ones with less priority are not encoded. So the lowest priority is towards the left here. This means that this bit, D1, has a higher priority than D0. And then again, D2 has a higher priority than D1 and D0, and D3, being the most significant bit, has the highest priority compared to everything else. In other words, if D3 is 1, then we don't care about the values of the other inputs, and the output is defined by D3. If D2 is equal to 1 and D3 is not activated, then we don't care about D1 and D2, and the output is this, and so forth, up until, of course, we reach the final case here where none of the inputs is activated, in which case the output is something that we have to ignore. We also call this an undefined output state, which implies that we need an extra output, the so-called idle output. If the output is 0, this means that you neglect the output. Otherwise, you do not neglect the output. Finally, before moving to the next slide, it is worth noting that unlike the previous slides, in this case, we do not ignore the first input, so there's no ambiguity with respect to that. Having all that said, now we can easily use these truth tables over here, alongside with a Carnot map, and build a 4-to-2 priority encoder. The way to do that is by starting with x over here and treating it as a function. This would be the Carnot map with all of its mean terms here. Now we care about these mean terms. And we have to be careful because the mean terms here are more than one, of course. If you're trying to think how many mean terms are grouped together in here, every mean term that has 1 as its most significant bit, and obviously if you have all the options here from 3 bits, that gives you 8 combinations. As for here, you got 2 bits, which means another 4 combinations. So overall, you are expecting to have 8 plus 4, 12 mean terms. And indeed, if you put all the mean terms here from the complete truth table, if we expand everything that you have here, it will look like that. We can do the same thing, of course, for y. And this is how the kernel map would look like. And this is how you would group together the mean terms. And as a result, you would get this. The minimal sum of products would look for x like this and for y like this. Of course, this presupposes that you did we followed the same process for defining the idle output. You treated it as a function, you did a kernel map, and you ended up that the idle output is just ORing all of the inputs together. So that's the idle output. Which is bringing us next to the 8 input priority encoders. As you can see, the inputs over here, they imply priority. The highest priority is in I7, which has a higher priority compared to I6, and so forth, all the way to I0. You also have an enabling input. And as a result, you get 3 outputs here as a binary code. Then you got something called the group select. You can try to remember it as got something, which is the equivalent to the idle state. And of course, you got the enable output. Now, if you're wondering why you need those two, of course, this is used for cascading together 8 input priority encoders. But with skipping all the details, as you can see here in the schematic, we managed to cascade together 2 8-bit priority encoders by using the enabling output from over here as an input, hard coding it as an input to the second 8-bit priority encoder. Another thing that is worth noting is that the dot something over here is going to be the most significant bit to be outputted from this 16-bit priority encoder. Then this is how you get the second bit, by using an AND between A2 and A2 from here, from both priority encoders. Likewise, you do the same thing for the output N1, and for N0 you use A0 from here and B0 from here. And this is how it works. Now, as you can imagine, you can build more than just 8 input priority encoders by cascading more and more of the 4 input priority encoders. Finally, we've reached to the arithmetic and logic unit. This is going to be brief. This is wrapping up everything together from what you've seen in the previous lectures. You have the arithmetic and logic unit here that can perform several operations. You've seen them here: binary addition, binary subtraction, ORing, ANDing, or XORing. And these operations can take place on 2 different input streams, A and B here. And based on what you've been taught, you have a control unit here that sends a signal to the ALU and lets it know what to do, which of these operations to use on A and B. And the result will be the corresponding one that you see over here. Now we're going to let all the details out of your material because it's not worth getting in so much detail. What is worth noting is that it's easy to imagine that all operations are already built in inside an ALU. So you got addition, you got ORing, XORing, and of course you need a unit control here for all that to happen. And that was for today's lecture. See you in the class.